About Fisher projection, those who have come new, they will find it quite a bit difficult. Now, for that, let me in a very simple term, let me explain what is Fisher projection. Now, Fisher projection during the Fisher projection, when you write a Fisher projection, it is written in this way. That is, the molecule is written with four lines vertical to each other. Suppose you have a CHO here, CH2OH, H and OH. If you have a molecule, the this particular way of representation is exactly equivalent to the two bonds are pointing towards you, the horizontal bonds are pointing towards you, and the vertical bonds are moving away from you. This is what is meant by Fisher projection. That means none of the atoms except the carbon is in the plane of the board. Only this carbon is in the plane. These two are projecting towards you. These two are away from you. Okay, I will take the model and show it to you. See here, yesterday I made the model. I will switch on my video. Okay. Now see. Let me make it to the, I don't know whether I can, how to make it to the larger. Okay. Now see here. See, if I want to draw the Fisher projection, this orange one, the orange one is a CHO group. The top orange one is a CHO group. The down red one is a CH2OH group, bigger one. This is hydrogen, and this is OH group. I don't know whether you are seeing the right way. If you look from there, are you seeing the right way? Is this OH group to the way I have written in the board, on the board, or is it opposite? How do you see it? Because I'm looking from the back side. Is this on the this? See, if what I'm seeing on the right on the board, the OH is on the right side, but here is the OH right side to you or left side to you? Is this OH right or left? Tell me. Now let me exchange one second. One second. Now see, is this the same thing which I have drawn on the board? Just watch and tell me. This is the hydrogen. Here is a hydrogen, which I have drawn here. Hydrogen. This green one is the OH group, which I have drawn on the board here. And this one is orange color. Orange. And this one is red. Now see, this is pointing away from you. This also is pointing away from you. See the way I'm holding it. These are the horizontal ones. These are horizontal. These two are horizontal. These two are vertical. These two. The two the red and these two are vertical. So when you draw the Fischer projection, if you have the real molecule in your hand, you should hold it like this. You should not hold like this. That is the meaning. These two groups should not be closer to you. It should be away from you. So that is what is meant by Fischer projection. So the moment you draw the Fischer projection, let this figure come to your mind. This is the figure which has to come to your mind. Okay. Now see, if you rotate this vertically along this axis, 90-degree clockwise. If you rotate this 90-degree clockwise, see how it will look like. Just try to draw it yourself. Draw it first. You are rotating this molecule 90-degree clockwise. Draw in your paper how it will look like. I'll give you 2 minutes to draw it. Come on, take the paper, draw it by yourself. You are rotating this whole molecule along this vertical axis. Along this vertical axis. Remember, the axis is not passing through the bonds. It is passing only through the carbon. See here. I don't know whether you can see it properly. It is passing through the carbon. It is not passing through this this atom because it is away from you. So how will it will look like? You have drawn. Now see. Let me rotate it. I have rotated 90-degree clockwise. Now draw the figure. Now draw this figure. How it will look like? See, you got the CHO on the top, CH2OH down. Okay, CH2OH is down, and now you have this and this, which is pointing towards you, hydrogen, and which is pointing away from you, OH. Look at what has happened. See this. See this. You had the hydrogen here. The hydrogen was here. Now you are rotating it. It has gone towards you. That is, the hydrogen which is on the left has come to the right. See that. And the OH, which is in the front, has gone to the back. This is 90-degree rotation. 90-degree, not 180. Suppose you are going for 180-degree rotation. What will happen? Any 180-degree, front will come to the back, left will go to the right. 180-degree rotation, left will go to the right, front will come to the back. But here it is only 90-degree. The two CHO and CH2OH has come to the plane of the board. And the H and OH has gone to the back side. Now slightly you can rotate the whole molecule on the plane down. So that will give you the standard way which we are used to write the molecule. See here. This is the H, no change. OH, then CHO and CH2OH, CH2OH. So this is the molecule. Okay. Now see here. I can do one thing I have told you before. I don't know whether how many of you remember. You can exchange these three groups like this. The molecule will not change. Hydrogen can be brought here. This CH2OH can be brought to the place of the OH, and OH can be brought to the place of H. Remember, we are not mutually exchanging them. So it is just a rotation. We are not doing anything else. We are rotating this molecule along this axis. We are rotating, only rotating along this single bond. Along this single bond, we are rotating the molecule, and this leg I will use. There are three legs here. See here. The three legs are getting interchanged, mutually exchanged, one over the other. So H comes here to the plane. OH comes to the front. OH. And CH2OH goes to the back side. CH2OH goes to the back side. Now that means, see here, let me repeat the same thing here. I'm holding the CHO as such, no change. This I will bring here. This I can bring here. This I can bring here. Remember, molecule will not change. In a Fischer projection, this type of a rotation is allowed. CHO. H, CH2OH. And, oh sorry, not CH2OH, OH. Sorry. Here I should write OH. This is H, this is OH, and this is CH2OH. Okay. Now, if you want it, you can exchange. You can bring any of the group to any place you want without changing the molecule. What you have to do? Hold one of them. Now look here. I'm holding this. I'm holding that. I'm keeping the H there. Now mutually exchanging these three. So these are the things which you can do with Fischer projection, CH2OH. Okay, OH, no, CHO, CHO, and OH. OH. Okay. Now just wait for 1 minute, please. Just 1 minute. Okay. So you can interchange these groups in this way. Okay, so all these are representing the same molecule. These are the different fission projections of the same molecule. Which molecule? This molecule. Okay, so this is about fission projection. Now let us look at molecules containing two chiral carbons. Molecules containing two chiral carbons. Now the number of isomers, stereoisomers or optical isomers, number of optical isomers equals 2 to the power of n, where n is the number of chiral carbons. Number of chiral carbons in a molecule. Okay, so if you have two chiral carbon, there will be 4 isomers. If you have 3 chiral carbon, 2 power 3, 8 isomers. If you have 4 chiral carbons, 2 power 4, 16, 5, how much is 5, 60, 32, 6, 64, 7, 128, and 8, 256 forms isomers. See, if you have 8, if you have 8 asymmetric carbons or chiral carbons, there will be 256 isomers for it. A very good, and one of them, a very good example for that is cholesterol. Cholesterol, everyone knows what is cholesterol, right? Everyone knows what is cholesterol. The greatest villain today. Now there are you can write 256 structures for cholesterol. Okay, cholesterol is a steroidal molecule which you are going to study. It's a steroid. Okay, roughly this structure. I don't exactly remember what is the full structure, but I'll just give you a brief outline. Here is structure of cholesterol, approximate structure. You have two methyl groups here. Then cholesterol means you have OH here. And then I think you have a double bond over here. And then, yes. Okay, now you have chiral carbons here, here. Okay, this is chiral, all these, there are many chiral carbons. There are 8 chiral carbons on this. Okay, so you can write 256 structures. Out of this, only one is actual cholesterol. One compound only is representing the cholesterol. Only one possible structure is cholesterol, and this elucidation of this structure of cholesterol, finding out the structure of cholesterol, has resulted in 2 Nobel Prizes. 2 Nobel Prizes in chemistry. Okay, one Nobel Prize was given for proposing a structure, proposing the first structure with the chemical evidences. Oh God, what's wrong? Oh